One of my favorite machine learning models are decision trees just because they're fun to look at and really easy to understand and how to apply them. I find them fascinating. Now, in all fairness, you don't really see decision trees used in the field of computer vision or self-driving cars that I've seen, but it is one of the basics of machine learning that you kind of need to know about. So it's sort of the fundamentals of machine learning we're talking about here. You can't really expect to go into a job interview for a self-driving car company and not know about things like decision trees and some of the other basics of machine learning, even if you're not going to apply them in the real world. It's sort of just the common language that we talk about. And who knows, maybe there'll be some application for these that we haven't thought about yet in the field of self-driving cars. But they are a fun thing to work with, so let's dive into it. The idea is that decision trees are constructing this flowchart automatically to help you decide a classification for something with a machine learning system. So this machine learning system is called a decision tree. It's what we call another form of supervised learning. Basically, all machine learning systems are supervised, where you're giving it some sample data, and out come the resulting classifications. The output is this model that's given by a tree. So let's say we're trying in this example to figure out whether or not I should go play outdoors today. Maybe you're training it with a set of training data where 9 of the data points say, yes, you should go out and play, and 5 of them say, no, you shouldn't go play. The objective that the decision tree is trying to reach is to minimize the error at each stage in predicting whether or not you should play or not play, given some choice it can make at that stage in the tree. So for example, maybe we can start at the top with the weather outlook. Maybe if the weather is sunny, we go down this path, and if it's overcast, we don't go down this path, and if it's rainy, we go down this path. And basically, out of all the feature attributes that we have to choose from, the decision tree will choose the attribute that will minimize that error the best. So we know that if it's sunny, we can break down things further into 2 of them were decided to play and 3 decided not to play. And if it's overcast, 4 of them decided to go outside and none of them didn't. And there are some people that apparently decide to play in the rain. So I don't know, go figure. And as we move down further, the decision tree can say, okay, what other features do I have to look at? I can look at the humidity. Maybe that's in my training data as well. And the trick here is how to define what that breakpoint is in humidity that will minimize the error in predictions at that stage. Maybe I can converge on a value of 70% humidity, where if the humidity is less than 70%, I know I do want to play, but if it's greater than 70%, I know I don't want to play based on the training data. Maybe I can look at how windy it is as well, and I can also quantify the point at which I define it to be too windy. If it's too windy, then maybe I don't play, and if it's not windy at all, or not very windy, I do play. So at the end of the bottom of the decision tree here, we have all of these binary decisions where we actually end up with 0 error. We can say definitively that out of our training data, every single data point that got to this point in the tree had one result or the other, right? So for every training data set that I gave it, if it's sunny and it's really humid, I never play. If it's overcast, I always play no matter what. And if it's rainy, but if it's windy, I don't play. So you get the idea of how that works. The magic is in building up this tree automatically over time. So the decision tree model is trying to figure out which features to evaluate at each stage in the tree and how to make that decision as to which direction it should go, how it should branch, given the data that it has. And it builds this up automatically over time, just trying to minimize that error as it goes down. Let's say, for example, I want to build a system to evaluate resumes that are submitted for a job that I'm trying to fill. So I might have some historical database of hiring data where I know attributes that are on resumes and whether or not people were actually hired in the end. So I could create a decision tree based on this. I could train that decision tree based on that data and arrive at a machine learning system that will predict whether a candidate will get hired or not just based on the attributes of their resume. So let's dive into an example here. This is some totally fabricated data that I made up. It's not real. But here we have 5 different candidates that tried to get a job at my company. And we've actually tabulated their years of experience, whether or not they're currently employed, how many previous employers they had, their level of education, whether they went to a top-tier school, where they did an internship, and whether ultimately we decided to hire that person or not. Okay? First of all, we need to make sure that we convert all of our data into numbers because our decision trees like to work with numbers and not categories. So for example, level of education doesn't say BS and Masters and PhD. I've encoded that as 0, 1, and 2 instead. But after I train a decision tree on that, maybe I could end up with something like this. And this is actually what falls out of the data. First of all, did you do an internship? If you did, then it turns out that that person gets hired pretty much all the time based on the training data that we have. So based on this fabricated data, the most important thing is to do an internship. Followed by, are you currently employed? If you are, then that's also results in a hire. So if somebody else decided you're good enough to work for them and remain employed by them, that tends to be a good indicator as well, it turns out. Do you have less than one prior employer? If yes, then you just don't have enough experience for us, it seems, and that's a don't hire decision. But if you had more than one prior employer, then you do have a fair amount of experience we should consider as well. And we can further ask whether you went to a good school or not. If no, we don't hire them. And if yes, we do hire them. If this makes you feel a little bit queasy, it probably should. This is a good example of where you kind of need to think about the ethical implications of machine learning systems that you build. And the real scary part here is that this model is going to be biased by the data that you give into it. And I don't want to go off too much into an ethical rant here, but if you were to actually do this using real training data, any biases that exist within the people in your company would be reflected by this model, right? So there could be, subtle gender discrimination going on, or age discrimination, or even worse, that's just sitting there in your data that your model will uncover. And the good thing about decision trees is that it makes it really explicit what those decisions are. They're very easy to understand. So if you ended up with a box in your decision tree that says, is the person over 40, you could ask yourself some very hard questions at that point of, maybe there's age discrimination going on in my company, and I shouldn't really consider that in my hiring decisions. But going off on a little bit of an ethical tangent there. Anyway, the way it works, like I said, we're trying to, I described it earlier as sort of minimizing the error as we work our way down the tree. More mathematically accurate would be to say that I'm minimizing the entropy of the data at the next step. That's actually how we measure it from a mathematical standpoint. There is an algorithm that does this for us called ID3, and we can just use that through the packages that we have installed into Anaconda already. It's what we call a greedy algorithm. So as it goes down the tree, it just picks up the decision that reduces the entropy the best at that stage. So wherever it is at that stage in the tree, it just goes with whatever decision it can make to minimize that entropy at the next stage. Now that might not always be an optimal tree because we're only looking at one step at a time, but at the end of the day, it works. Now, just like we talked about k-fold cross-validation versus a single train test split, you can do a similar idea with decision trees. So one big problem with decision trees in general is that they're very susceptible to overfitting. All those individual decision points are very specific decisions that might be only informed by a handful of data points. So we can very easily end up with systems that are overfitted to the data that we gave it. Even when using k-fold cross-validation, it's just a really big downside of decision trees. Now to fight this, we use something called random forests. So the idea here is that we randomize the process of building our decision trees a little bit. So we have a bunch of different alternative decision trees that are fitted to our training data, and we let them all vote on the final classification. So we can randomly resample the input data for each tree that we're training it on, and a fancy term for that is bagging or bootstrap aggregating. And we can also randomize a subset of the attributes that we have available to choose from while training each individual tree. So maybe some attributes are actually withheld from different trees, and that will prevent it from overfitting on that specific attribute. So by withholding some data and randomly resampling the data across all these different trees, we end up with this broader variety of decision trees, some of which may be overfitted in different ways, but by letting them all have a crack at the data and voting on the final outcome, they as a whole can prevent overfitting. So you see this forest is greater than the sum of its trees, if you will. Anyway, let's dive into an example and see decision trees in action. Like I said, it's kind of hard to think of an application for this in the field of self-driving cars, but it is an important machine learning technique to understand and know about just to be conversant in machine learning. So let's dive into another fabricated example and see how it works.